Today's lecture is on testing whether a number is prime or not. To prime or not to prime? That is the question. This is Dr. Eduardo Dueñez at UT San Antonio. Mathematics just never makes it too easy to deal with prime numbers, does it? So it turns out that it's actually a lot easier to come up with algorithms to certify that a number is composite. And in some ways, these algorithms, as we will explain later, can be used to ascertain that with high probability, a number is prime if it is prime indeed. Um, Actually proving that a number is prime algorithmically cannot is hard to do efficiently. We'll discuss that at the end. For now, we will start with approaches to ascertaining that a number is composite in an efficient manner. So as a starting point to trying to find a test for compositeness, um, what we do is go back to our old friend Fermat's Little Theorem, which in the classical form it stated says that when n is a prime number, then the congruence a to the n congruent to a mod n holds for all integers a. This statement could never be used to prove that a number n is prime because it is a theorem whose whose hypothesis is that n is prime. However, if we write it in contrapositive form, the conclusion of this theorem is going to be that n is not prime, therefore that is composite. So that's going to work as a test for compositeness. So the contrapositive form of Fermat's Little Theorem is the following. So if an integer n and some other integer a satisfy that a to the n is not congruent to a modulo n, then we can conclude that n is composite. So now this becomes a theorem whose conclusion is that n is composite. And the integer a is called a Fermat witness of the compositeness of n. As a first example of the application of the contrapositive form of Fermat's Little Theorem to prove compositeness, consider the composite number n equals 341, which factors as 11 times 31. Let's forget for a minute that we know that this number is composite or that we know anything about its factors. And let's start looking for Fermat witnesses of its compositeness. So if we try the base number a equals 2, and we do 2 to the n modulo n, we do find that 2 raised to the 100 to 341 is actually congruent to 2 modulo 341. So what does this say? It does not give any information, any useful information. All that this is saying is that the contrapositive form of Fermat's Little Theorem is giving us no information because the necessary condition in which the congruence is not satisfied is simply not holding. However, in keeping the search for a witness, we could go, say, to a equals 3. And in that case, we do 3 to the n, 3 to the 341, and we find that it is congruent to 168, not congruent to 3, modulo 341. So this is already enough to show with certainty that 341 is composite. But as a very important observation here, notice that this is a certificate. A equals 3 is a Fermat witness. It certifies that 341 is composite, but it gives absolutely no clue as to the factorization of 341. So this is a peculiar state of affairs, and it goes with the territory of efficient testing for compositeness, which can be done as we are trying to do with a first step is the Fermat test. But the factorization of a composite number is cannot, to the best anyone knows yet, be done efficiently. So there's a big gap between showing that a number is composite and actually finding its factors. Let's give a second example to test the effectiveness of Fermat's criterion for compositeness. So consider the number n equals 561. Let's not say more about it for the time being. And let's try and look for Fermat witnesses. You could take values of a equals 1, 2, 3, up to 561, and you would see that each of those numbers fails to be a witness for a Fermat witness for the compositeness of the number 561. In other words, insofar as Fermat's little theorem goes, 561 is behaving exactly as if it were a prime number. However, 561 is composite. Factors as 3 times 11 times 17. So this speaks to the limitations of Fermat's test for composite numbers. Some composite numbers can simply fool it. Thus, this number 561 is an example of a composite number n which has no Fermat witnesses. So these composite numbers are kind of like really pretty clever numbers in that they can fool Fermat. So if you have a to the n congruent to a mod n for all possible a's and a certain fixed value of n, such as 561, then that value of n is called a Carmichael number. And you would say, well, but you know, how likely is it that we are going to have a lot of numbers n that really quack and walk like a prime insofar as Fermat is concerned? Well, there is an important and famous theorem going back to 1994 by Alford, Granville, and Pomerantz, then that in particular it gives that there are infinitely many Carmichael numbers, of which the first few ones are 561 from the previous slide, 1105, 1729, etc. But the list goes on and on ad infinitum. So that is a sad state of affairs in that we could be fooled using the Fermat test into thinking that composite Carmichael numbers are actually primes. So it is not a foolproof test for compositeness. But all hope is not lost. Actually, a fairly simple refinement of Fermat's little theorem is sufficient to develop a surefire test for compositeness. So even if Fermat's test fails, it can be refined, and that's what we're going to talk about right now next. All right, so now we talk about this theorem that is a refinement of Fermat's little theorem. So Fermat's little theorem starts with the hypothesis that you have a prime and then certain congruences are satisfied, right? So let's get the prime p equals 2 out of the way. So consider odd primes. And so for these odd primes, we're going to have some type of congruence. So let me explain, right? So a prime greater than 2 is necessarily odd, and any odd number, so let's write p, the odd number p can be written as 1 plus an even number, correct? But that even number may have multiple factors of 2. So write your prime p as 1 plus 2 times 2 times 2 times 2 as many times as necessary times an odd number q equal to 1, 3, 5, 7, some odd number, right? Now, so if a now is assumed to be a number coprime to p, then we have two mutually exclusive possibilities. The first one is that a raised to the power of q is already congruent to 1 modulo p. The second possibility is that when you do the list of numbers starting with a to the q, then you square this number to get a to the 2q, Then you square this number to get a to the 4q, etc., up to getting to a to the 2 to the k minus 1 times q. One of these numbers is congruent to minus 1 modulo p. Let me make the remark here immediately that if we were to extend this list all the way to a to the 2 to the k times q, 2 to the k times q is equal to p minus 1. So the last element missing on this list is a to the p minus 1, which is already known to be congruent to 1 modulo p by Fermat's Little Theorem. So what this theorem is saying is that either the first element of this list of numbers is already congruent to 1 modulo p, or this list of numbers, which eventually is going to lead to one last thing congruent to 1 modulo p, this list of numbers at some point has a negative 1, which of course when squared immediately gives a 1 after. So it's fairly easy to see that this theorem implies that Fermat's Little Theorem in the form a to the p minus 1 congruent to 1 modulo p, but it refines it in these two different ways. One possibility or the other must occur. So before heading to the proof of the theorem, let's prove a very simple lemma to the effect that if an integer x satisfies the congruence x squared congruent to 1 mod p, where of course p is a prime, then necessarily x is congruent to plus or minus 1 modulo p. So congruences modulo a prime p sort of work the way you would expect from your experience in other fields, which that's what z mod p is. So the proof is very simple because x squared congruent to 1 modulo p is the statement that p divides x squared minus 1, which factors as x minus 1 times x plus 1. So because p is a prime, it must divide one of the factors, either p divides x minus 1, so x is congruent to 1, or p divides x plus 1, so x is congruent to minus 1 modulo p. All right, so let's actually proceed to the proof of the theorem proper now. So the proof actually, the theorem is a generalization of Fermat's Little Theorem. So it's not surprising that the proof starts with Fermat's Little Theorem itself. So when p does not divide a, that's a hypothesis, a is co-prime to p, we must have a to the p minus 1 congruent to 1 modulo p. But because p minus 1 is equal to the 2 to the k times q, right? So we have this congruence, a to the 2k q is congruent to 1 mod p. What we're going to do next is start with a to the q and successively square it. So consider b equals a to the q. And as I said, consider the sequence starting with b squared, with fourth, etc., up to b to the 2k minus 1 and b to the 2 to the k. Of course, we want to regard this sequence as a sequence of residues modulo p. So the main thing to note here is that this last term of the sequence, right, is b to the 2 to the k, which is being a to the q, correct? This is a to the q times 2 to the k, which as we had seen, my Fermat's Little Theorem is congruent to 1 mod p. So the last term here, b to the 2 to the k, is 1 modulo p. And in this, the way this sequence is being obtained, as I remarked, is that each term is the square of the prior one. So, of course, the last term is equal to 1. If at any point you had a term equal to 1, then all of the successive terms are going to be equal to 1. So one possibility is that the whole sequence is the sequence, it is congruent, consists of terms that are congruent to 1 modulo p. So they could all be congruent to 1 modulo p, starting with b itself. Now b is actually a to the q. So if the sequence starts with B congruent to 1 modulo Q, then we are in the first possibility of the two, the either or. So we are in the case of the either A to the Q is congruent to 1 modulo P. But the other possibility is that the sequence ends with 1, of course, as we said, but the sequence is not always equal to 1. So that means that at some point you have one term of the sequence somewhere, immediately which is equal to 1, but immediately preceded by something that is not equal to 1. But what the lemma says, because the relation between successive terms is one of squaring, if a term is equal to 1 and it's the square of a preceding term which is not equal to 1, then the preceding term has to be minus 1 modulo p. So since the last term is equal to 1, that minus 1 has to occur somewhere before getting to the last term. So that's the second possibility. When not every term is equal to 1, then one of the terms must be a minus 1 that immediately precedes a 1 and so on. So that's the second possibility of the lemma, and that concludes the proof. So next, as promised, we are trying to get an algorithm that proves that a number is composite that is more powerful than Fermat's test, which, as we saw, can be fooled. So based on the previous theorem, there is an algorithm known as the Miller-Rabin test, which uses the contrapositive of the previous theorem to come up with an algorithm that finds witnesses of the compositeness of an integer, right? So so consider an of course, even in the question whether an even integer is composite or not is not very, it's just a very simple one. It's either equal to 2 and it's prime, or it's an even number greater than 2 and therefore it's composite. So let's assume from here on that we are considering an odd integer n, which of course we can write in the same form, 1 plus 2 to the k times q. And the algorithm, if n is composite, is going to try to find a witness of the compositeness of n, right? So for this, we just, the first step is simply to generate a random integer a. This is going to be the a in the theorem, right? Between 0 and n. This this means that, you know, a is either, well, okay, so let's see. So if a is not coprime to n and it's a number between 0 and n, then we already have found something really interesting about n, namely that it has to be composite, right? Because it shares a factor with a number in the greater than 0 and less than n, correct? So in that case, the algorithm certainly can output that n is composite and terminates. So that's a very boring and very lucky case in which you found a factor of n before even starting the algorithm. Otherwise, we do exactly as we did before. We take b equals a to the q modulo n. All of this is going to be arithmetic modulo n. So we consider b. If b is equal to 1, then we are in the first situation of the theorem, and then there's nothing that we can say. The algorithm is simply inconclusive. So we end at least this particular trial with this particular a value of a is inconclusive. Otherwise, we start constructing the sequence starting with b and squaring as follows, right? So we're going to be looping, constructing b to the 0, 1, 2, 3, up to k minus 1, correct? So we start with b itself. If b is congruent to minus 1 modulo n, again, the test is inconclusive because there's nothing here that is inconsistent with the hypothesis that n is prime. So the test is simply inconclusive. And then, but if it's not equal to -1, congruent to -1 modulo n, then we square this b and we go back to 1. So we, in other words, yeah, all right. I'll do some discussion later. And if after doing all of this looping, we never reached an output of inconclusive, so in other words, if all this loop ended without terminating, then we can surely say that that the number n that we started with is composite, and the number a that succeeded in proving that n is composite is called a Miller-Rabin test of compositeness for n. So let's talk a little bit about why this algorithm works. So you see here, we're looking at the sequence of powers of b, correct? So either the sequence is all ones, right? Or if the number n is prime, then the sequence would at some point reach -1 and then 1, 1, 1, 1, 1, and so on. But so what? What happens in the other case? In the other case, what will happen is that we never reach a -1. But remember, no matter what happens, because we're starting with a number called prime to n, right? If we would be expecting, if n were prime, that we end at 1, and before getting to that 1, we will necessarily get a -1. So if a -1 is never found, then that is inconsistent with the assumption that n is prime. So n must be composite. So I'm not going to go into more of a discussion as to the correctness of the algorithm, but it should be pretty clear that it is a straightforward application of the previous theorem. So we'll leave it at that. Just some quick remarks. Again, I would like to stress that these tests can, both Fermat's test and Miller-Rabin, certainly, can only ever really prove that a number is composite. They cannot ever prove primality. And the other thing is, it should be pretty clear that this test is strictly stronger than Fermat's test in the sense that a witness of compositeness of n already serves as a Miller-Rabin witness of compositeness. The converse is not true, as we're going to show with a couple of examples next. So the question still remains, how effective is the Miller-Rabin test is in detecting composites? As we saw, Carmichael numbers can fool Fermat's test. Is Miller-Rabin's test better? The answer is yes, absolutely. So there's this theorem that we're not going to prove, but it goes as follows. So if you have a composite number n, of course odd, goes without saying, then as a matter of fact, at least 75% of the numbers between 1 and n minus 1, right, are actually Miller-Rabin witnesses of the compositeness of n. So it's very easy to simply, by picking A at random, to find a witness of the compositeness of n. There will always be witnesses of the compositeness, and they're actually plentiful. We do not know a priori what those witnesses are. So that's kind of a problem, but it's actually pretty easy in practice to find them because 3/4 of the numbers A are witnesses. So another way to put this, the content of this theorem, this is saying exactly the same thing in different words, is that if you apply the Miller-Rabin test and it comes out as inconclusive, when you're choosing the numbers A at random and you do it 1 time, 2 times, 3 times, 4 times, many times, capital N times, right? Let's say, I don't know, 50 times, then the probability that N is prime is at least 1 minus 1/4 to the N. In other words, the probability that N is composite is tiny. is 1/4 to the n, because if if n were composite, then 75% of the numbers a would work in each instance. So that's that means that the probability that n is prime is really very large if it passes many Miller-Rabin tests, in the sense that they come out inconclusive. So at least from a probabilistic point of view, um, we can have extremely large certainty that a number n is prime by applying Miller-Rabin multiple times. But this is not a test of primality with absolute certainty, only in a probabilistic sense. So let's consider an example of Miller-Rabin, just to show how much better it is than Fermat's test for compositeness. So consider the Carmichael number 1789, which is of course composite, 7 times 13 times 19. It has no Fermat witnesses at all, being a Carmichael number. But it turns out that about 90% of integers in the range, from 1 to n minus 1, are Miller-Rabin witnesses of the compositeness of n. So let's work out how this turns out to be, right? So the first thing is we write the number n as 1 plus a power of 2, in this case 2 to the 6 equals 64, times an odd number 27. So the exponent k equals 6 and the q is equal to 27, right? Now let's try a equals 2. So what happens when you do a equals 2? B is equal to 2 to the 27, which is congruent to 645 modulo n. Then when you square b, you get b squared congruent to 1065, and then you square again and you get b to the 4th congruent to 1. Because we reached a 1 without first having been on a -1, this proves that n is composite, and a equals 2 does serve as a witness. Similarly, a equals 3 gives a b of 664, and then b squared is congruent to 1. So again, it's a 1 preceded by something other than plus minus 1. So a equals 3 is also a witness. And similarly, 4, 5, 6, 7, and 8 are witnesses of the compositeness. Now, the first couple of values of a that turn out not to be witness are a equals 9, where b equals 9 to the 27 is already congruent to 1. So it's inconclusive. And therefore, a is 9 is not a witness. And similarly for 10 to the value of b is 10 to the 27, which is -1. And therefore the test is inconclusive, because a -1 is immediately preceding a 1. So there's plenty of Miller-Rabin witnesses of the compositeness of the Carmichael number 1789. So as this illustrates the point that Miller-Rabin can't be fooled by most choices of A, will actually serve as witnesses. So a very natural question to ask is, well, if Miller-Rabin is so great at proving that a number is composite, isn't it conceivable that rather than choosing A at random, there's a systematic way of testing a few A's that for sure will find that the number n is composite? And if not, then it necessarily will have to be prime. So it turns out that this question is extraordinarily deep, just extraordinarily deep, as it connects to, well, not just the Riemann hypothesis, the most famous open problem in pure mathematics, but in fact, a stronger version, the so-called generalized Riemann hypothesis. As much as I would like to go into the discussion of this, and it's a topic really close to my heart, I'm going to have to leave it at that. This is an incredibly outstanding open problem in pure mathematics. It's believed to be true by most mathematicians. Uh, and if the answer to this, the generalized Riemann hypothesis is yes, if it actually turns out to be true, then it can be shown that a composite odd number, any composite odd number n, will have a Miller-Rabin witness in a fairly short interval. In an interval of polynomial length, right, squared, on the number of bits of n. So put it in a different way, if you test all of the a's in this range and none turns out to be a witness of the compositeness of n, then definitely n will have to be prime. Now, so this would be an amazing thing to know, and it is in all likely true. So in all likelihood, if you start doing Miller-Rabin with 2, 3, 4, 5, 6 values of a, and if you stop after 2 times log n squared steps, and you didn't find a witness, then any sane mathematician in the world will say, okay, yes, it does have to be prime, because there's no way the generalized Riemann hypothesis is false. However, because the generalized Riemann hypothesis could actually be false, then we cannot know for sure. So we have this algorithm that in all likelihood is polynomial and efficient, but we cannot prove that it is so. The only proof of this known is conditional on the generalized Riemann hypothesis, and it points to the incredibly deep arithmetic facts about integers. So this is a really interesting situation. Amazing algorithms, seems to work in practice. It will work in all the cases that you know, but you don't have a mathematical proof that it does. And it will likely not in our lifetimes. That's how difficult proving the generalized Riemann hypothesis is likely to be. So what do we know about unconditionally and efficiently proving that a number is prime? So as a matter of fact, it was only a few years ago, in 2002, where the first deterministic polynomial time algorithm to prove primality was discovered by Agarwal, Kayal, and Saxena. So, and the theorem says that the test that proves that n is prime can be done in, roughly speaking, the log of n, which is the number of bits of n raised to the power of 6. Actually, the power of 6 is not quite enough. You need 6 plus epsilon. But that's polynomial time on the size of the input. So this is unconditionally polynomial time algorithm. However, 6 power is really quite bad. An algorithm with exponent 4 is not considered practical. So this is really not very practical. So in although there have been refinements and have managed to lower this complexity, in practice, it is still more efficient to use algorithms that involve randomized parameters, um, but that still can unconditionally prove that a number is prime. In fact, later in the semester, we're likely to find one of those algorithms involving elliptic curves. So stay tuned.